Assalamualaikum and good day everyone. From the previous session, you have seen a pole assignment regulator where we actually design a controller in a system in an adaptive manner where the controller can actually ensure the stability of your system by designing a set of desired pole for your system. At the same time, we have designed a regulation where the polynomial C in the noise in your system is being cancelled out to actually improve the performance of your system. In this session, I'm going to explain an extended version of our pole assignment regulator. So we're going to actually have a sort of a servo following where your reference is actually being tracked. Okay, so how to do that? So for example, we have a reference that need not to be zero but need to be tracked by your controller. So let's have a look at this plan where we have a plan output corrupted with uncorrelated noise zeta again. Okay, and then we have our plan actually being described by an ARCS model. Y is equals to b over a polynomial b over a multiplied by your input u, okay, plus c multiplied by zeta. That polynomial c is the unwanted polynomial for your noise. Okay, so the objective of this exercise, the first one is actually to remove the noise polynomial c at your in your output. Okay, and number two is actually you want to track the reference rt at steady state. Okay, so this is a servo following concept. All right, okay, so have a look at this system. So in the beginning, this is your system where you have input u applied to your system with the transfer function of b over a. You have z minus k there as the delay to the system, and then you are having a disturbance added to the response of your system. So what we want to do is that we will allow the noise to be added, but we want to cancel the polynomial c in this system. All right, so looking at that polynomial a, it is actually a polynomial of 1 plus a1z minus 1 plus a2z minus 2 plus and so on and so forth until an z minus n, depending on the model order of your system. And the b is starting from b node, okay, plus b1 z minus 1 until bn z minus n, depending on the model order of your system. And similarly for your polynomial c, it is 1 plus c1 z minus 1 and so on and so forth until cn z minus n, depending on the order of your system. Okay, so what we want to do, we want to design a controller. Let's say how to do that. Okay, let's say we want to actually design a controller in both part. Okay, the first part on the feed forward. Okay, I'm going to design a controller there on the feed forward where I have my controller defined as h z minus 1 divided by f z minus 1. So this is actually a polynomial h and f as the controller in the feed forward section. Okay, at the same time I will remain the controller similar from the previous exercise where we have the controller as g over f with a negative sign there. So that controller is actually a negative feedback to our system with the polynomial g over f. Okay, so what we want to do is actually we want to design this controller so that it is cancelling our noise polynomial c from the response of our system. At the same time, it can also ensure the stability of the system by designing a set of desired poles. And number three is actually we want to make sure that our output is tracking the reference that we give to our system, which is RT here. So we want YT is equivalent to our RT. Okay, so this is what we want to do. I will derive for you the equation that we have done here to get the closed loop system equation. Let's have a look at the system that we have just now. So I have the ARCS model system, okay, with z minus k b over a, and then input u is applied to it, and then the response y is actually correlated with noise zeta multiplied by polynomial c over a. Okay, so from this equation, we would like to design a controller with an extended pole assignment controller. So what we want to do is actually the controller is looking like this. At the feedback, I'm going to add similar controller like what we have earlier, which is a g over f. Okay, So that G over F is going to be substituted, is going to be added to a summing point with a negative sign. So I can just take out that negative sign from the block diagram and put it in the summing point. Okay, and then before we add the reference signal R into this, we are designing another controller at the feed forward of our system with a transfer function of H over F. Okay, so then that input R is added added into the transfer function H over F before it can be added into your summing point here. All right. Okay, so this is your controller. So the blue line is actually the design controller for your system. Okay, so what we can do then, we can have a look at the system and then try to derive the closed loop system equation. So if you look at U, just rewrite that. Okay, so if you look at U signal is actually now equivalent to RH over F minus YG over F. Okay, at the same time we have for our Y is equals to UZ minus KB over A, or I can put that U at the back, U plus our C over A zeta. That's your Y. Okay, so we're going to substitute a U into equation of Y, okay, to get the overall closed loop system equation. So then I will have Y from the second equation. I will have Y is equals to Z minus K B over A multiplied by U, which is RH over F minus YG over F plus C over A zeta. Alright, so we can then try to expand this equation and collect all the terms of with Y together. So I'm going to have AFY is equals to okay, so that is if we multiply everything with AF, so that's what we're going to get. And then I'll collect all the terms with Y together. So I'm going to have AF plus Z minus KBG Y equals to, I have Z minus KBH with R plus CF with zeta. Okay, then from there I can rewrite in terms of Y again. Y is equals to Z minus K BH with R plus CF with zeta. The whole lot is divided by AF plus Z minus K BG. Okay, so now this is your closed loop system equation. All right, with the parameter of with the characteristic equation is the same as before with the pole assignment regulator, which is AF plus Z minus K BG. Okay, so again as before, we can assign this characteristic equation to a set of desired poles that you want, which is in this case, let's say is T. At the same time, to cancel the polynomial C, what we want is we can also assign this as C there, CT. Okay, so in order when we do that, what happens is that your characteristic equation will become Z minus K BHR. This is over CT plus this part also CFZ divided by zeta divided by CT. So that polynomial C will be cancelled out at your noise. Okay, but you can see that there is a polynomial C there. So we will see that will be actually affecting our controller H later on. Okay, when we derive our controller H later on. But the most important part is when we design this kind of controller. Okay, what happens is that our system will remove the polynomial C from the noise. At the same time, we will set the system to be with a desired set of pole T, so that the system will always remain a stable system. So again, with this unique solution, you need to for a unique solution, you need to follow this regulation, where your model order NA plus NF must be equivalent to NB plus NG plus K, and it is must be equivalent to NF plus NG plus 1. It must be more than your NC plus NT. So with that, I further derive that this is the first rules that you have to follow for your model order F, and then this is the second one that you need to follow for your model order for G, okay, for parameter polynomial G. Using this equation, you can later define the model order for your F and for your G, and then from there you can actually use the previous equation for your characteristic equation to find out what is the value for your controller F and controller G for the feedback of your system. Okay, that is for your feedback controller. Okay, what about the feed forward controller H? Okay, feed forward controller H is coming from also by changing the characteristic equation to CT. Okay, so this is what you have decided just now from the design rule. We have changed our characteristic equation into the value of CT. Okay, so when we do that, what happened if you look at this closed loop system equation on the other side here? Okay, so let's have a look at that equation. Right, so when you change the denominator with CT, so what happened? The Z minus K BH, okay, will also divided by CT plus CF zeta also divided by CT. Okay, so the first part, the second part here is alright, because that is what you want. You want to cancel the polynomial C at your zeta, at your noise, so that you have noise become a white noise. So this is really good. Okay, but the other side here, you have create a Z minus KBH also divided by CT. Okay, so on that part, you want your input to be your Y over R must be equals to 1, because you want it to become a servo following, isn't it? You want your output to follow the reference signal that you give to the system, the input. All right, so in that, having that in mind, what you want is that you want your Z minus K BH over CT also equivalent to 1, okay, with all the Z in there we equate with 1. So this is what we have here. Okay, so that's what we have there. So from there, from this equation, I can write H is equals to CT divided by Z minus KB, all right? Okay, Z minus KB, we can do that, right? We can then equate all the Z in the equation to be 1, to be equivalent to 1. Then we can put the polynomial C and our polynomial T into this equation, and then from there we can then find out what is the polynomial H, or what is the gain H for this system. Okay, so that's how we want to design this extended pole assignment. I will show you the example of this, so that it will make you very clear on how it is being utilized in terms of solving a problem. Let's have a look at this example. This is an example of extended pole assignment regulator that you need to design for a problem that is shown in this equation. So you have a system with YT is equals to Z minus 1 minus minus 0.5 Z minus 2 divided by A. So this is your polynomial A. Okay, so that's your polynomial A. Okay, that's your Z minus KB. This is your polynomial C. All right, so this is the problem. So when you design the pole assignment with regulator, so you need to find out first the value of your model order A, B, and C. So if I define that again for our system, this is your polynomial A with the highest order. The model order is model order 2. Okay, And then for the second part, when we have z minus 1 minus 0.5 z minus 2, this is your z minus kb. So if I split that, okay, factorize it by z minus 1, the remaining will become 1 minus 0.5 z minus 1. Okay, what I did was, for this part, I simply take out z minus 1. So I just have 1 minus 0.5 z minus 2. Why do I do that? Because I know that this is my z minus k, the delay of our system, and this is the polynomial b. We need to split it into two. Okay, so that's what we have here. So from there we can tell that k is equals to 1 and your model order b is equals to 1 as well. Okay, so then lastly, have a look at this polynomial c, your noise. Okay, at your noise, all right, polynomial c is equivalent to 1 minus 0.4 z minus 1. Okay, so from there I know the model order for my C is 1. Okay, then again we want to design a system with a stable pole. So from the problem it says, it is stated that we need to design a controller, okay, extended pole assignment, when we have the pole is decided at a single pole of z equals to 0.7. Okay, how to do that? We know that roots of our poles is actually z equals to 0.7. Okay, so this is a pole, so it must come from our characteristic equation. So if I write that z minus 0.7, it must be equals to 1. Okay, because that's how we get this is initially when we want to get the roots. So from here, when we get the root, it become like that. Okay, that is the roots. So it's the value of your pole. Okay, so if we then divide this equation with z, okay, so that we can get the value of z minus 1. If we divide by z, it means simply similar as if we multiply with 1 over z, or 1 over z minus 1. 1 over z. 1 over z, sorry. Okay, so what we do is that we multiply both sides, left and right, with 1 over z. So I'll get, for the first one, z divided by z, it become 1. 0.7 divided by z, it becomes 0.7 z minus 1. Okay, this is the whole purpose. I want to convert it into a zero order whole. Okay, so this is equivalent to 0. So this is your t in z zero order whole domain. So this is your polynomial t. Okay, so I'm going to use that later here, right? And model order for my t is 1. Okay, so with the new controller, I will use the similar, okay, the similar design rules, okay, which I have just now. F ut is equals to g yt plus hrt, okay, where the design rules that I have to follow is coming from my characteristic equation. AF plus Z minus KBG must be equals to CT. Alright, so then before I can actually find out what is the polynomial F and polynomial G, okay, I need to find what is the best model order for them so that we can get a unique solution. So for F, just follow this equation here. NF is equals to NB plus K minus 1. Okay, so from there, by substituting the value, we get NF is equals to 1. Okay, similarly, so from that, when we have NF equals to 1, we can just say that our polynomial F is equals to 1 plus F1Z minus 1. Of course, the value of F1 we need to find further later on. Okay, what is the value of F1? Okay. Okay, similarly for polynomial G, I'm going to put this requirement of NG must be equals to NA minus 1. So since NA is equals to 2, therefore my NG must be equals to 1. So from there, I will put that into my polynomial of G, where G started with G naught plus G1 Z minus 1. Of course, the value of G naught and G1 we need to find from our characteristic equation later on. Okay, so there are three values that I need to find. What is my F1, what is my G naught, and what is my G1. Okay, so I need to find that from my my design rules from our characteristic equation. Okay, so looking at that, we look again at our characteristic equation, substitute all the polynomial into this equation. So I have A multiplied by F multiplied by plus Z minus K multiplied by B multiplied by G, okay, which is equivalent to C multiplied by T. So when we when we have this equation, we need to expand it, and then we're going to compare the coefficient from left hand side to the right hand side. Okay, so what we're going to do, similar like before, okay, I'm going to expand this equation. So this is how I got expanding the equation, and then I'm going to compare the left hand side with right hand side. Okay, right, so when I'm comparing the coefficient, I'll compare Z minus 1 first. Okay, so when I compare Z minus 1, what do I have on the left hand side? I will have, this is the first one, F1, okay, plus G naught. Oh, there's another one here, minus 1.2, 1.2. So I put that into equation. F1 minus 1.2 plus G naught is equivalent to my right hand side, which is minus 0.11. Okay, so that's the first coefficient. The second coefficient that I'm going to use is Z minus 2. So for Z minus 2 on the left hand side, I will have 0.85. Okay, 0.85 is there. Okay, and then I'm going to have minus 1.2 F1. Minus 1.2 F1 is here. Okay, and I'm going to have 0.5 G naught here. Okay, minus 0.5 G naught. And then I'm going to have G1. Okay, there. Okay, G1 there. Okay, on the other side, I only have 0.28 Z minus 2, so that is equivalent to 0.28. So by comparing this coefficient, we'll be able to solve the value that we need. Okay. Lastly, don't forget to compare the coefficient of Z minus 3. So for Z minus 3, I have on this side 0.85 F1. Okay. And the other side, and there's another one is minus 0.5 G1. And on the left hand side, this is on the left hand side. On the right hand side, I have it nothing, so I don't have anything, so it is equals to 0. Okay, looking at these three, I have three unknown to solve, which is F1, G naught, and G1. Okay, so there are three unknown. I have three equations from Z minus 1, Z minus 2, and Z minus 3. So therefore, I can solve this problem. Okay, so by using substitution, you can use substitution, or you can put this all in your calculator and then use the formula, and then you can actually solve this for the three unknown. And I've done that, I've solved it. Okay, and it is equals to F1 is equals to 0.56, G naught is equals to 0.62, and G1 is equals to 0.884. Okay, then knowing these three unknown, substitute back in the polynomial that we have developed earlier. So for F, it is equals to 1 minus 0.5 to Z minus 1. So sorry, this is 0.52, okay, Z minus 1, okay. And then for G naught, it is equals to 0.62 minus 0.884 Z minus 1. So this is for your polynomial F and polynomial G. Okay, so you have done the controller on your feedback feedback controller. Okay, so what about the next one? What about your H controller? Okay, because you know your system, the new controller is actually having the value of H as well, isn't it? Okay, so if I can just write here, there's a H there. Okay, add it to your U. Okay, so you've done your G over F already. Okay, mind you, for this F is the same as the F that you have obtained earlier. Okay, for the feed forward controller is the same F as you have obtained earlier. All right, so you want to actually find out what is your H. According to the rules that we have developed earlier, H is equals to this equation here. So H is coming from this equation here, okay, where you have your H is actually given by that equation. But when you substitute z equals to 1 into this, of course z minus k also will become 1 because z is equals to 1. All right, and then you're going to have your equation becoming t1 divided by b multiplied by your polynomial c. Okay, so you're going to have your equation as t with the value of z equals to 1 divided by b with the value of z equals to 1 multiplied by the polynomial c from your system. Okay, so this is your controller h. Okay, so we're going to use that in our problem just now. Okay, so I'm going to put that t1 means t with the z value become 1, okay, divided by b with z the value become 1 multiplied by polynomial c. So if I look at my polynomial t, what I'm going to do is I'm going to substitute the value of z, equate it with 1. So what I have is that when I put z equals to 1, I will have 1 minus 0.7. So t1 is really becoming only a value of 0.3. Similarly, for b, z minus 1, if I put value here with the z equate with 1, so z inverse z minus 1 also will become 1. So I will have b1 is 1 minus 0.5, which is 0.5. Okay, so your b1 is 0.5. Your polynomial c, you don't have to do anything about it, just multiply it with the equation. So put that into your equation here, t1 divided by b1 multiply with polynomial c. So I have 0.3 divided by 0.5, and then I just need to multiply with that with my polynomial c. So my h controller will become 0.6 minus 0.24 z minus 1. Okay, how do I get that? 0.3 divided by 0.5 multiply with polynomial c. Okay, so that's all for your controller. So you can then put back your value of controller in this closed loop diagram here. Okay, then you should be able to solve your problem with the 3 things that you need to solve just now. The first one, you want the poles to be stable poles. So by the design of poles equals to 0.7 just now, you'll be able to get it as a stable system. Number 2, you want to remove the polynomial c from your zeta. You've done that. Okay, so you have actually here you should have a polynomial c, isn't it? Okay, your zeta here. Okay, but when you've done this controller, that will be cancelled. The polynomial c will be cancelled. So you're going to have a white noise only. There's no polynomial c anymore in your noise. Number 3, you want your reference input following your output to be the same as your reference input. So yt is equals to rt. So you get that by doing the first part here with having the controller as h over f. Okay, so you've done that. This is your controller with the polynomial that we have actually obtained from this example. Okay, so in conclusion, what you want to do is actually first you want to have what we call pole assignment and also zero assignment regulator. Okay, then also known extended pole assignment regulator. What you want to do is remove the noise, okay, the effect of noise in the polynomial from the polynomials by removing polynomial c from your zeta. So it's been removing it from the output, and then you want to shift your open loop poles to a design of stable poles. Okay, and then you want to have your output to track the reference of your system, which is your RT. Okay, so you want YT to be equivalent to RT. Okay, with that summary, you have concluded the development of extended pole assignment, or some books might call it a zero end pole assignment controller, and this is one of very important controller for adaptive system. Okay, with that, thank you very much, and I will see you in the next video.